Hey guys, welcome to Computer Science 318 class. In this class we're talking about algorithms and we're trying to analyze them, okay? So today we'll be talking about exhaustive search. Exhaustive search, let's go. Okay, so what is an exhaustive search? Remember when we were talking about the brute force approach, right? So what does that mean? Brute force means solving the problem the most intuitive way, which most likely is not going to be the most efficient. Okay, that's going to be brute force. So usually when I think about brutal, right? So that usually means something which is very hardcore without any thinking. Like when I'm being brutally honest, right? So I sacrifice the aftermath, the consequences. I don't really care about them. I'm brutal, right? So I'm hardcore. That's what brutal means. Now, exhaustive search is another way of solving a problem, which is very similar to brute force search, where it may be different. So exhaustive search means that you're going to create a combination of all possible ways, of all possible solutions, and you're going to try each one of them. Okay, so it's similar, but not necessarily the same as a brute force approach. Again, exhaustive search means searching for something exhaustively, trying all possible combinations, trying all possible answers. For example, if let's say I'm asking you, so what is I'm thinking about a number between 1 and 10, guess what the number is, okay? And I will give you a hint, it's my birthday, okay? So maybe a smart way would be to get into my records and for example, okay, so my birthday, I don't know, is like 10th, May 10th, right? So in this case, it gotta be 10, right? That would be maybe a smart way. A brute force, an exhaustive search way would be to come up with all the numbers between 1 and 10 and just brutally ask me like if that's true or not. So for example, 1. Is it 1? I would say no. Is that 2? No. Is that 3? No. Is it 4? No. Like, is it 5? No. Is it 10? Yes. Okay, and then now you guessed it. Okay, so again, without any thinking, just create all possible answers, all valid answers, and ask me if that answer is right. That's what brute force search means. Okay, so let's dive into that brute force exhaustive search. Exhaustive search, sorry. Okay, let's give a definition. Okay, so exhaustive search it is simply a brute force. By the way, again, I highly recommend you taking those notes as well, because in this case you will memorize the definitions and you will need those definitions for the quizzes and for the exams. The brute force approach to combinatorial problems. It suggests generating each and every element of the problem domain, selecting those of them that satisfy all the constraints. Okay. And then finding a desired element. Okay. Then finding a desired and generate each and every element of the problem domain, selecting those that satisfy all the constraints, and then selecting I guess, yeah. And then finding a desired element. Okay, cool. Perfect. Okay, so for example, let's talk about the problem, which is very no, hold on. Okay, let's talk about a problem which is very popular in computer science. It's TSP, or traveling salesman problem. Very, very popular problem in computer science. Highly recommend Googling that as well, or just like maybe recommend it on YouTube. You will see that. Anyway, so I'm going to paint. Let's say we have a couple of cities. Okay, so let's say I don't know. So let's say that's Florence. Let's say that's Columbia. Florence, Columbia, Charlotte. I'm talking about South Carolina, North Carolina, okay? and then let's say Charleston, I don't know, somewhere here. Okay. So we have, and let's say we have roads between each one of them, so we can consider all the pairs. And let's say I know the distances between them, and let's say there would be, okay, I'm gonna use an example from the book. So that would be, let's say, okay, there will be two, I don't know, let's say like 200 miles. I don't know, there'll be 3. This guy will be 7. Okay, this guy would be 8. Okay, now this guy would be 5. And this connection, the distance would be 1. Okay. Yeah, so the travel salesperson basically says that how can you go from one city, let's say from Florence, how can you visit each one of the other cities, sell some of the stuff, right? So travel and salesman problem. Yeah, and visit each city exactly once, only once, and then come back. Okay, so for example, do you go from here to here to here to here over there? Or do you go, let's say, from here to here to here to here and there? Or like vice versa, do you go from here to here to here to here, for instance? Okay. Yeah, it turns out that it is a very, very difficult problem to solve. And unfortunately, as of now, in this kind of stage, to the best of my knowledge at least, nobody figured out a way to solve it better, to solve it simpler than just trying all possible combinations, which is exhaustive search. Okay, so that's a travel salesman person problem. Okay, so the problem asks to find the shortest tour through a given set of n cities. Okay, so we're given n cities that visits each city exactly once. Exactly once before returning to the city where it is started. Okay. Okay. So when I draw this figure, when I draw this map, does it remind you of anything else? Is there anything else which you learned before which this stuff reminds you of? If you're thinking about, hey, focus. Okay, thank you. If you're thinking about graph, weighted graph, you're correct. That should be weighted graph. Okay, so this can be modeled as a weighted graph. Okay. Is a weighted graph with vertices representing, okay, so vertices at the points are those dots, right? So what do they represent? They represent the cities, right? The cities. And edge weights specifying distances. Okay, cool. So yeah, so we have a weighted graph, and basically we need to find yes, and then we will need to find so-called Hamilton circuit. So Hamilton circuit is basically like exactly what I described, right? So how to traverse all the nodes exactly once and then come back. Yeah, and when it comes to the graph, it's called the Hamilton circle. It's a technical term, Google that, although it's not that important as of now. Okay, cool, yeah. So question, how would you solve it, right? And again, since we're talking about exhaustive search, right? So what is the kind of the way to solve it exhaustively? A way to solve it exhaustively is just to consider all possible paths, all of them, right? So what kind of paths do we have when we go from here, visit all nodes exactly once and come back, okay? So we consider all of them, and then we just compare them and find the one which is the shortest. That's it. So that's, yeah, so that's kind of how it works. So let's try to do this. Okay. So let's call, I'll be using notations in the book. Okay, so they'll be called A. They'll be called A. They'll be called B. This will be called C. And this will be called D. Okay. So let's talk. Let's start. I'm gonna solve that as an example. So if the tour is A, B, C, D, A, okay? So we started at A and then we'll go A, B, C, D, A. Okay, what are we gonna have? We're gonna have 2 plus 8 plus 1 plus 7, which is equal to 18, right? Okay, it's not equal to, right? So I'm gonna use this sign. Okay, let's say our route is A, B, D, C, A. Okay, in this case, what are we gonna have? 2 plus 3 plus 1 plus 5, which is equal to 11. Okay, so that's a lot better. The first one was 18. That this one is 11. This one sounds like a lot better. Then third one is A, C, B, D, A. Okay. 5 plus 8 plus 3 plus 7 is equal to 23. Okay. Next one, A, C, D, B, A. Okay. A, C, D, B, A. That gives us 5 plus 1 plus 3 plus 2, which is equal to 11. Okay, that's good. Okay, so this 23 out of question. This 11 is good. This 11 is good. Okay. Then A, D, B, C, A gives us 7 plus 3 plus 8 plus 5 equals 23. Okay, that's also out of the question. And then last route, A, D, C, B, A. Okay, that gives us 7 plus 1 plus 8 plus 2. That gives us 18. Okay, perfect. So in this case, we see two optimal solutions, 11 and 11. So those are the ones. Okay, so that's pretty much how it's done. So this route is optimal. Okay, second one and fourth one, those routes are optimal. Okay. Yeah. Okay. So Hamilton circle. Can be defined as a sequence of n plus 1 adjacent vertices. Okay, why n plus 1? So here we have n vertices. We start with 1, let's say with A, and then we come back to A as well. So which means that A is mentioned twice. That's why it's n plus 1. Where the first vertex of the sequence, okay, the first vertex of the sequence is the same as the last one, and all the other n-1 vertices are distinct. Okay, so this Hamilton circle, or this the TSP, travel and salesman problem, assumes that you have roads between each city, right? So basically, if I create one more city, then you're gonna need to have the route, the kind of the lengths, the distances between this city and all other cities. Okay. Okay, so n-1 vertices which are distinct. Okay, we can get all the tours by generating all permutations of n-1 intermediate cities. Okay, then compute the tour lengths. Compute the tour lengths and find the shortest ones. Okay, or one length. Okay, find the shortest ones. Okay. Perfect. Okay. So the question is how many of them do we have? Like how many tours we have? So in this case, we have 4 cities, 1, 2, 3, 4, 5, 6, and 6 paths. Okay. So this problem grows even quicker than exponentially. It's a factorial problem, right? Well, factorial. Well, yeah. So the total number of permutations. So was the total number of all possible combinations, right? Is n-1 factorial, okay, over 2. Okay, what does that mean? That means you can solve exhaustively. You can solve that problem exhaustively only for very, very small numbers of n. I heard somewhere that there was one supercomputer in China and it solved this problem that particular way, right? So the like the brute force search, this problem for 80 cities, okay? And it took it 2 years. 2 years to do that. Not sure if it's true or not, but that's what I heard. So it's n-1 factorial over 2, basically. Okay. That's the idea. And find. Yeah, perfect. So that's exhaustive search. Okay. Moving on. Another problem which can be solved exhaustively using exhaustive search, and there is another way of solving that which we'll talk about later, and that's called knapsack problem. Knapsack problem. Okay, so basically in this case, the scenario we have is the following. It's one of the probably the funnest problem to solve. You have a burglar. The burglar breaks into the house and he has a knapsack. So he has a backpack. That backpack, let's say, can at the most hold, I don't know, 20 pounds. So the burglar breaks into the house. He sees like all different values. He sees that, okay, so that thing costs like, I don't know, $2,000 and the weight of it is like 1 pound. That thing costs like, I don't know, $20,000 and the weight of it is like, I don't know, 30 pounds, something like that. So he's given a set of different goods, and he, assuming that he knows the price, so he calculates the price like in his head. So he knows the prices to each one of those particular goods, and he's thinking, okay, so what out of all of those goods, which one of them should I put in my backpack such that I will carry out, such that I will steal the biggest amount of values, the biggest amount of money? Okay, make sense? So that's knapsack problem. Okay. Yeah. So how would you solve it? Basically, you can do exhaustive search. Okay. What does that mean? That means you can just create all possible combinations of all the goods in the house, right? And then decide which one of them, well, first off, will fit into the backpack, which one of them is not too heavy, okay? And which one of them contains the biggest amount of money, which one of them he can later sell for the biggest amount of money, because that's probably the whole reason. A burglar breaks into the house, he wants to steal the biggest amount of money, okay? Cool. So given n items of known weights omega 1, I'll be using omega, but I'll be saying W, but you better say omega. Omega 1, omega 2, omega n, and values V1, so basically you have weights, right? So let's say in pounds, okay, and then you also have values, which is how much money each one of those items costs. Values V1, V2, and so on up until Vn, okay. And a knapsack of capacity big W, okay. You need to find the most valuable subset of items that fit into the knapsack. Okay, that's the idea. Cool. So let's take a look at the example. I'll be using the book. Example from the book. Okay, so okay, so let's say I have a knapsack. So that's its like capacity, that's its weight. So I can fit at most, let's say 10 pounds. Okay, 10 pounds. Okay, now items. I have only 4 items. So the first item, okay, well, no, let's do, okay, so that's the first item. No, hold on. Yeah, okay. That's the first item. That's second item. That's third item. And here's the fourth item. Okay, so imagine I broke into the house and there are only 4 things I can steal. Okay, which is of course not possible. Well, it gotta be like a very, very poor house. What's the point of doing that then? It's not worth it. Okay, so the weight of the first one is 7 pounds, okay, and the value is 42 bucks. Okay, now for the second, the weight would be 3 pounds and the value would be 12 bucks. Okay. Okay. Now for the third one, the weight would be 4 pounds and V3 40 bucks. Okay. For the fourth one, 5 pounds, 25 bucks. Okay. So the question is, I only have 10 pounds like in a knapsack. What should I steal, right? Such that I will have the biggest cost. The biggest amount of money stolen, and also I would have they would fit into 10 pounds. Okay, that's the question. Oh, okay, so how would you solve it? You would basically, again, you would try to solve them this way. Let me. Okay. Okay, so imagine I steal only the first item. In this case was the value 42 pounds, right? Then only the second item was the value 12 pounds. Okay, imagine I steal only, so the subset, right, contains only the third item, was the value, okay, 40 pounds, sorry, 40 bucks. Okay, was the fourth one. Okay, then I'm gonna have 25. Okay, and now I can think about different combinations. So let's say, what if I steal 1 and 2? What if I steal 1, 3? Okay, what if I steal 1, 4? Okay, what if I steal, let's say 2, 3? Okay, and I'll just keep writing here. Okay, what if I steal 2, 3, 2, 4? What if I steal 3, 4? What if I steal 1, 2, 3? What if I steal 1, 2, 4? Okay, I'm just writing all possible combinations since it is exhaustive search, right? So let's say I can't really come up with any other smarter way of doing that, right? So what if I steal 1, 3, 4? What if I steal 2, 3, 4? And what if I steal 1, 2, 3, 4? Okay, So in this case, I enumerated all possible combinations, all of them, right? So basically, and now, like if I try to sum up the values, right, what I will find is that this option is obviously the most expensive one, right, because like I'm accumulating all of them, so 42 plus 12 plus 40 plus 25, right, so that's like definitely the best one. However, what's the weight? 7 plus 3, that's already 10, plus 4 plus 5, I cannot do, like, I'm not gonna fit that, right, so that's like not feasible. Okay, so there is no way for me to actually make it work, make it happen. Okay, so if I, let's say number 1, of course it's 7, that'll work. Number 2, it's 12, that's only 3 pounds. Here it's only 4, that's only 5. Okay, that will all work. Now 1, 2, I think that will also work. It'll be 52 pounds. Okay, so that'll be 52. Now 1, 3, okay, 7 plus 4, that's not gonna fit into 10 pound knapsack. 7 plus 5 is also not going to fit. Okay, so basically if I calculate all of them and if I eliminate all options which weigh too much, I will see that the option number 3, 4, like with the third item, the fourth item, I'm gonna have the biggest amount of money I will steal. Yeah, 3, 4, okay, which will be $65. And the capacity will be, the weight of the whole thing will be 9, which is going to fit into my 10 pound knapsack. So that's the idea. That's the idea behind it. Okay, again, so I generate all possible solutions for my problem, and I find the one which fits into my knapsack and which is the most which gives me the most expensive value, the biggest value. Okay. Hope it makes sense. Let's get back to exhaustive search. Okay, so the exhaustive search approach leads to generating all subsets of set of n items, computing the total weight of each subset in order to identify feasible subsets. Okay, and finding a subset of the largest value. Okay, so again, we identify all the subsets, all possible subsets, then we eliminate all of them which do not fit into our backpack, and then we find among the ones which are feasible to carry out, to carry away from the house, we identify the one which is the most valuable, which is this one. Okay, cool. Okay, so how many of such combinations do we have? 2 to the n. 2 to the n, where n is the number of subsets. Number of items. Okay. Yeah. Okay. So let me know, by the way, if you don't understand why it's 2 to the n. But at this point, you should. Okay, cool. So that's what we call exhaustive search. That's a set of problems. I highly recommend reading the book, read everything which is there about those two problems. That way you understand them a lot better. And also there is one more problem which I'm not going to cover here. It's called the assignment problem. Okay, that's also actually a lot of fun to solve. Yeah, cool. Exhaustive search. Hope you guys enjoy that. I'll see you next lecture. Bye.